In this lab tutorial, I will introduce a technique to measure the cutoff frequency using a digital multimeter. So let's look at this simple RC circuit. Firstly, let's calculate the cutoff frequency theoretically. The output voltage is across the capacitor. So let's look at the S-domain circuit. The impedance for the resistance is R. The impedance for a capacitor is 1 over SC. The transfer function of the circuit is defined as the output voltage over the input voltage. HS is equivalent to V output over V input. The resistor and the capacitor is in series. So that is typically a voltage divider circuit. The voltage across the capacitor over the source voltage should be the impedance of the capacitor over the total impedance in the circuit. So the numerator and denominator are multiplied by S to get rid of the S in the denominator and divided by R. So we get the numerator is 1 over RC. The denominator is S plus 1 over RC. This circuit is typically a first-order low-pass filter. S plus 1 over RC, so the cutoff frequency should be the constant term in the denominator. So 1 over RC is 1 over 1000 ohm times 0.1 microfarad. So that is 10K reading per second, 10,000 reading per second. To calculate the cutoff frequency in Hertz, so we should use ohmic C divided by 2 pi. 10 over 2 pi is 1.59 kilohertz. So here, theoretically, the cutoff frequency should be 1.59 kilohertz. So let's try to measure the cutoff frequency of the circuit. Firstly, we need to build the circuit and connect the power supply to the circuit. So resistor, capacitor, and here is the power supply. Red lead and black lead. We're going to change the frequency of the power supply. So it doesn't matter what's the initial value for the frequency. So we need to connect the output terminal of the function generator. But here we need to adjust the amplitude for the output signal from the function generator. We don't want the output voltage to be too low. So here, let's click on amplitude. Right now it's 100 millivolts, so it seems to be kind of low. Let's make it like 2 volts peak to peak sinusoidal voltage. So the next step, we need to connect the power supply to the digital multimeter. So the red lead should be connected to the positive terminal to the power supply. So here's the black lead. In the circuit, we just connect the output of the input of the digital multimeter to the power supply of the circuit. So here we just want to record the input voltage amplitude. So let's turn on the digital multimeter. So we connect the leads of the digital multimeter across the power supply. So we can turn on the digital multimeter. So here's the AC circuit. So we need to click on AC voltage. So here's ACV. Then shift decibel. So here is we make the input voltage as a reference. So the magnitude of the input voltage has been recorded by the digital multimeter. So right now it's 0 decibel. Now we need to connect the input of the digital multimeter to the output voltage of the circuit. So we just need to connect it, the two leads across the capacitor. That's the output voltage. So here we switch the lead of the digital multimeter here. So now it's across the capacitor. We try to measure the output voltage. So now we need to change the frequency of the power supply to make the gain of the circuit as 3 decibel below the passband gain. So here, let's increase the frequency. Notice that this is a low-pass filter. So when the frequency goes up, the gain of the circuit goes down. So right now it's 1.5 kilohertz. The gain of the circuit is negative 2.9 decibel. So we just adjust the frequency to make the gain of the circuit as 3 decibel below the passband gain. So it should be negative 3 decibel. So right now, when the frequency is 1.536 kilohertz, the gain of the circuit is below 3 decibel below the passband gain. So let's calculate the error percentage. The measured value is 1.536. The nominal value is 1.59 kilohertz. So the percentage error we calculated based on measured minus nominal over nominal. That is negative 3.4%. Should be negative 3.4%.